Okay, so I think we can get started now that more people have joined. Um, Hello everyone, and welcome to the third webinar of the FAME webinar series. Today, Lior Limonad from IBM Research will present Unlocking the Mystery of Business Processes with AI-Empowered Situation-Aware Explainability, or SAX. And before Lior gets started, just a couple of housekeeping notes that the webinar is being recorded. We're going to upload it on our YouTube channel and on our Learning Center in the next few days. And of course, feel free to type any questions into the chat, or we can have a Q&A session after the presentation. So without further ado, Lior, the floor is yours.
Thank you. I'll close my own window to not make it awkward that you are looking at my video in two different places. Hi, and welcome to this online webinar, which will cover work that was conducted by IBM Research as a partner in the FAME EU project. My name is Lior Limonad, and I'm a senior researcher at the IBM Research Lab in Haifa, Israel. The work presented here is part of my team's effort to leverage technologies in advancing the use of AI across various aspects of business automation. More concretely, I will be presenting work related to the development of solutions for explainability in business processes, which we refer to as SAX. This work has been carried out over the past couple of years within the context of the FAME project, with technological implementations designed to be enabled as analytical services that can be deployed and shared via the FAME platform as exchangeable assets. So, what is a business process? While definitions may vary slightly across the literature, a business process is typically described as a series of tasks or activities that, when executed in a certain order, work toward achieving an organizational goal, such as providing a service or creating a product for customers. The various sequences that can be followed in this context are usually described in a process model, which can be visualized using different graphical notations. One of the more common notation, which has also become an industry standard, is BPMN, as shown in the illustrated figure. We will revisit this particular process example in a few slides, but generally, a process model resembles a graph structure with nodes representing tasks to be executed, decisions to be made throughout the process, and arrows indicating the order in which the tasks may proceed. The need to manage business processes throughout their life cycle has led over the years to the formation of the discipline known as business process management, or BPM. Originally, BPM included basic capabilities focused on the design and execution of business processes, gradually expanding to incorporate more sophisticated abilities to discover, monitor, and improve these processes. Technological advances in computation have further enabled organizations to adopt tools that help automate these efforts, optimize resource usage, and maximize business profits. More recently, advancements in the field of artificial intelligence, or AI, have opened new frontiers, enhancing accuracy and efficiency in process execution, and as a result, reducing the extent of personnel needed for business process management. However, when AI is applied to process management tasks such as predicting the next activity, estimating completion time, or forecasting costs, the reliance on AI becomes a critical factor in the business. And consequently, as with the employment of experts, organizations must build trust in these AI technologies. Torini et al. Identify four aspects of trustworthiness: fairness, explainability, auditability, and safety. Fairness technologies aim to detect or prevent discrimination and bias across different demographies. Explainability technologies focus on providing stakeholders, including end users, with clear and interpretable explanations of the outcomes in a human centric manner. Auditability technologies enable third parties and regulators to supervise, challenge, or monitor the operation of the process. And safety technologies ensure the process operates as intended, even in the presence of active or passive malicious attackers. In the context of BPM systems powered by AI, explainability in its broader sense is regarded as a key functionality to be built into BPM systems by design. As such, explainability is also at the center of our research. It plays a crucial role in fostering users' trust and consequently promoting adoption and usage. This necessitates the development of solutions that can automatically generate human interpretable explanations for potential inquiries from customers and the individuals managing the system. Specifically at the intersection with processes, this capability becomes crucial for explaining why a process concluded with certain desired or unexpected outcomes, or why a product was created or shipped within a specific time frame and at a certain quality level. Here are a couple of examples. Consider a process for approving mortgage applications as illustrated. Such a process might involve an initial application review, followed by a credit check and property appraisal, before reaching a decision on whether to approve or reject each application. Suppose a customer submits an application and a few weeks later receives a rejection notice. In such cases, it is highly likely that the customer will expect the notice to include some explanation for the decision. Such an explanation could help the customer understand the reasons for the rejections and what steps, if any, they might take to resubmit the application. Here we have another example. The process associated with issuing a fine to a vehicle parked in a prohibited area. The typical time it takes for municipality officers to issue a parking ticket ranges from 10 to 15 minutes. However, certain cases may take longer, particularly during busy traffic times when a tow truck is required. Municipality management teams who oversee operations across different regions of the city may occasionally want to understand why it takes longer to issue a parking fine in a certain area or specific times of the day. This insight could help them identify potential interventions to expedite the process. Recent advances in AI and the emergence of complex models, such as deep neural networks, have led to the development of techniques and tools designed to identify how various input attributes fed into AI models correspond to their results. These tools are collectively referred to as explainable AI or XAI in short. Applying state of the art XAI to the context of explaining business processes involves using process logs that record historical process executions as input for constructing a machine learning model, also known as a surrogate model, which aims to mimic the process model and differentiate between various execution outcomes that require explanation. For the predictions generated by the surrogate model, are then passed to an XAI model, which provides explanations for specific instances by highlighting the significance and effect of various process-related attributes on the outcome. To achieve this, the mechanism underlying the XAI model attempts to create neighborhoods of cases that share similar characteristics, producing comparable process execution results. However, a key challenge with such an approach is that conventional XAI methods are agnostic to whether input combinations represent valid and legitimate process instantiations or happen to violate process constraint, potentially resulting in unrealistic or impossible scenarios within the specific process domain. So, recapping on the drawbacks, there are a few shortcomings when trying to employ state-of-the-art explainability techniques for the purpose of making explanations about business processes. Particularly, state-of-the-art explanations generated fail to express the business process model constraints, fail to include the richness of the contextual situations that affect process outcomes, fail to reflect the true causal execution dependencies among the activities in the business process, and fail to make sense and be interpretable to human users. In the following slides, I will elaborate on the essence of each of these limitations and will then present how we are attending to each, reviewing several ongoing efforts which have led to the establishment of what we call SAX in short. Thus, we introduce situation-aware explainability as a new discipline that bundles a set of newly developed techniques to tackle the listed shortcomings. So, what is SAX? SAX is a bundle of technologies developed by IBM Research in FAME to address the limitations just presented, with the aim to generate more adequate explanations about business process conditions, leveraging recent advances with AI. Key components in SAX are being gradually released as open source via the SAX for BPM library that will be demonstrated in the last part of this webinar. So, to generate effective explanations for processes, I will now address each of the listed points, elaborate on the challenges, and explain how we approach solving them. The first drawback is about making explanations that fail to meet the characteristics and constraints of the business process at hand. What does it mean that many explanations fail to express the process constraints? This means that current solutions are agnostic to the flow control, or what we usually refer to as decision logic or gateways that unfold along the execution of business processes. Not all process executions are alike in terms of the sequence of activities carried out, and as a result, when trying to reason about certain process outcomes, not all activities and not all activity-related information is relevant or contributes to the outcome being inquired about. For example, say we are trying to investigate the possible reasons for delayed processing of mortgage applications. It may also be that none of the process executions that correspond to delayed applications have been affected by the preliminary screening step at which demographic information is reviewed. Existing XAI is somewhat agnostic to such conditions in process executions, leading to the generation of explanations that may include attributes that do not truly affect the extended duration of process execution. Therefore, we need to develop smarter mechanisms that will be able to take into account the process flow control and filter out information that is not relevant or that does not coincide with the outcome for which an explanation is needed. To address this kind of problem, we looked into the internal working of an existing XAI tool such as Line. When trying to establish a relationship between a given input, in this case being a tabular representation of all the various variables that unfold during process execution, and associating it with a handful of results, say whether the mortgage is approved or rejected, the tool will consider all the rows containing all the variables in the input. Here, as a resolution, we adjusted the inner algorithm of Lime to first filter out all the rows in the input that reflect process execution traces that are inconsistent with the outcome investigated. For example, if we know that demographic information is encoded only for the cases where a mortgage application is approved and is otherwise ignored, we exclude the cases in the log that include this information and then let Lime execute only with the part that the log is relevant. As a result, the explanations only include attributes that may truly affect the decisions to reject mortgage applications. You can read more about this developed solution in a paper, the one cited on the slide, which was published in the PMAI 2022 workshop that was hosted by the ICHKAI conference. A second point is complementary to the previous, which is on augmenting explanations with contextual information instead of stripping off irrelevant information. Let me explain this in more detail. Sensible explanations may sometimes fail to include important information related to the broader context, or one may say, the external circumstances in which decisions are made during process executions. Such information may not be captured in the plain log of the engine executing the process, requiring additional inference about ad hoc circumstances or what we refer to as derived events. These inferences sometimes involve the use of external data sources to piece together all the information that was actually considered when decisions were made. For example, a bank account manager deciding whether to approve a mortgage application may also be influenced by the overall workload piling up during high season periods or by occasional managerial guidelines to expedite the rejection of overly delayed applications. Existing XAI tools may overlook such crucial information if it is not included in the original input recorded by the system. To address the need for enriched input in XAI, we explored utilizing the functionality of complex event processing, or CEP, engines to complement the conventional operation of a business process execution engine. The core idea is that using a CEP engine enriches the data provided as input to the XAI model, resulting in more accurate and meaningful explanations of process executions. With CEP, we can embed rules to infer theoretically possible contextual conditions, allowing them to be considered for their impact on process execution outcomes, both in real time and retrospectively. For example, the CP engine in our case detects situations such as an application remaining in the system for more than 5 days. This information is then fed into the XAI algorithm, providing the user with a more comprehensive explanation that takes such conditions into account. Through this effort, we demonstrated that blending inferred situations derived by a CEP engine with traces of business process executions produces an enriched event log. This enriched log enables better situation-aware explanations compared to using the original event log alone. Revisiting the list of failures, the third one is a fundamental activity that relates to the essential need to generate explanations that are inherently sound. In this context, our effort focuses on the need to produce explanations that reflect the true causal execution dependencies among the various activities in the business process. For example, consider the basic three-step process illustrated, where after the decision point to approve a mortgage application, it is already determined that an email notice will be sent to inform the client, and the application will also be archived. Both subsequent activities are triggered once the decision is made to approve the application. The fact that the email is sent much quicker and earlier than the archiving occurs is incidental, possibly due to the archiving location being geographically more distant. While from a temporal perspective, archiving occurs after the email is sent, there is no causal dependency between these two activities. For instance, sending the email earlier would not allow the overall process to be completed faster. Misinterpreting the sequence as implying a causal dependency could lead to incorrect conclusions about how to optimize the process. So, in this particular example, from a causal point of view, the dependency among the activities has more of a tree form, as illustrated here, showing that both sending the email notice and archiving of the application are dependent on the point at which it was decided to accept the mortgage application. The question is whether we can figure out this while looking at the information within the process logs and potentially being able to infer from the historical timing of the activities these kind of dependencies. Luckily, with recent advances in the area of causal discovery, we have managed to develop an algorithmic approach that help revealing such dependencies. The developed technique is described in a paper being currently under revision titled The Why in Business Processes, which is hopefully going to see light soon. How do we then use the information in the log to determine such relationships? It is known that if one activity causes another, the causing activity will occur earlier in time. An activity that occurs later cannot be a cause to one that occurs earlier. However, we can uncover the nature of these relationships by leveraging additional characteristics of the timing of activities in the log. This allows us to determine whether X causes Y causes X, or if there is no causal relationship between them. We achieve this by making certain assumptions about the correspondences between the timestamps of various activities in the log. For instance, the fact that time progresses only in one direction allows us to consider the timing of a later affected activity as having a functional, typically linear relationship with the timing of its causing activity. Additionally, a certain degree of noise is typically present in realistic processes. It is reasonable to expect that the spread of activity times will not follow a normal distribution, as it is less likely for activities to be extremely expedited, while delays are more plausible. With a few adaptations and by conforming to these assumptions, we can apply a basic algorithm such as Lingam, which was recently developed to discover causal relationships between numeric variables in general, to conclude whether the execution of activity X causes the one of Y or not based on a given process log. The use of causal discovery can reveal various interrelationship causal structures. According to causal theory, three basic structures may be identified as illustrated. When the dependency is mediated by the occurrence of an intermediary activity, this is referred to as a mediator pattern. When the effect is mutually triggered by a common causing activity, this structure is known as confounder. And when an activity is caused by more than one activity, this structure is termed a collider. Any more complex causal network structures can be described as a composition of these fundamental structures. Why is it important to embed causal process AI in the context of process explainability? The key point is this. Many of the explanations we aim to generate are intended to provide a better understanding of the potential consequences of interventions and to guide decisions about modifications that could improve processes. Relying solely on traditional process discovery, which identifies associative relationships between activity execution times, may be sufficient for monitoring and controlling execution deviations. However, this approach needs to be complemented by techniques like the one we developed, which can provide sound answers to questions such as what might happen if we expedite or delay a particular activity in the process. Last but not least is the importance of creating explanations that are interpretable to users who are, in most cases, humans best suited to communicate through natural language. Many XAI tools are designed to identify which data attributes contribute the most and which contribute the least to predicting the condition for which an explanation is sought. For example, in the hazardous parking process, a bar chart like the one illustrated might show that the activity of filling out the hazardous circumstances by the officer has the greatest impact on cases where the overall processing time exceeds the usual duration. Contrary to this, the region in the city where fines are issued might be identified as the least significant factor affecting such delays. Now, consider a dataset where the number of attributes is not 4, as in the present chart, but rather in the hundreds. According to the typical 80-20 Pareto principle, in most cases, no more than 20% of the attributes are likely to be relevant. Presenting a chart with hundreds of variables would become extremely difficult for users to interpret effectively. Our approach focuses on finding the needle in the haystack by synthesizing all the available knowledge we can uncover about the process and integrate it to pinpoint at the aspects of the process that most significantly influence the condition being explained. So, for the given hazardous parking example, our explanation may become the statement highlighted, making it clear that the submission of an extended fine step in the process that includes the documentation of hazardous circumstances is the main factor contributing to delays in fine processing. Technically, we employ a developed methodology we call FBI, which stands for Form, Blend, and Interpret. The main idea is to blend different knowledge ingredients that address various shortcomings previously identified and input them into a large language model, such as ChatGPT, to generate explanations. The LLM produces a textual narrative articulating the reasons behind the question at hand. This includes the process knowledge ingredient, which incorporates process model constraints and contextual situations that influence process outcomes. The causal model ingredient, capturing the true causal execution dependencies among the activities in the business process, and the XAI knowledge ingredient, which reflects the relative importance of the attributes of the activities within the process. These knowledge ingredients are synthesized by the LLM to generate a natural language explanation that meets the requirements for clarity, coherence, and interpretability for human users. We wrapped the core of the previously presented capabilities as services as part of the SAX for BPM library released as open source on GitHub. This includes services for the discovery of causal processes, contextual enrichment, XAI for processes, and NLP for explainability. The library is being developed in Python, and we also created a basic Streamlit demo UI to show the basic of its usage, given a process event log as an input. So in the remaining of this webinar, I will give a short demo of the usage of the developed SAX for BPM library using the basic Streamlit UI that we developed. Okay, so let me give you a brief overview of the SAX for BPM library. The library can be accessed on GitHub via github.com/IBM/SAX for BPM. And once accessed, you can get the explanation, the homepage of the library, which also includes a few useful links, the installation instructions, a few tutorials, and also a link to the Python package. In order to set up the environment, you can either clone it to your development environment, or you can do a pip install. Once you have that, as I have here, you can see all the corresponding folders part of the library. The core of the library includes the causal process discovery folder, process mining, which is actually utilizing the PM4PY open source, the XAI part, and the synthesis with the LLM. Particularly for the current demo, I'll use the default Streamlit UI page, which was created to play around a little bit with the library and initiating the main services that it has to offer. Also, you can find here within the uploads folder the parking fines log file, which corresponds to the example that I've presented earlier. And we will use that file to inspect it and see how we can use the library to analyze it. So to start the Streamlit UI, the first thing you need to do is run the Streamlit run command, and once you've done that, we'll get to the main page of the UI, which gives a brief explanation of the package. And this is also where we can import the data from the log and do the various examinations. So I'll be uploading the log file I've just shown you. Here it is. Once we have selected the file, we'll do perform analysis, and this is now showing the log file with its various attributes. And then we can go directly to the process view, which under the hood has actually executed the process mining algorithm, which now shows the process model. We can examine the process model, and also we can get a list of its various variants with the corresponding number of traces. And we can also inspect the model which associates with each of the variants, and we can alter between the different variants here just to take a look what each one looks like. Corresponding to the selection of a variant, we can now initiate the causal discovery to see what the causal discovery model looks like. This is initiate through the analysis view. And again, the discovery was just executed under the hood, and now we have a comparative analysis view that shows us on the left-hand side the process model, And on the right-hand side, we see the causal model. The same screen also gives us a few insights that are automatically derived from the comparative analysis of the various discrepancies, the differences between the two graphs, from which one could infer a few insights as the ones that were presented earlier in the presentation. And as a last part, the UI also gives us the possibility to interact with an LLM to present a few queries about the process. For example, I can tick the process view, which under the hood will prompt the process model as part of the input preceding the query. And we can inquire about the process, any question, for example, which activity may be affecting the overall execution time of the process. Once we click analyze, the query is taken to the LLM, and we are getting the reply with the answer to our query. The answer takes into consideration the process model that was preceded as part of the input. We can repeat the same kind of interaction, but this time I'm also ticking the causal view. So this time the input in the prompt will include both the process model and the causal model. And now clicking to analyze the query will present a reply from the LLM, this time one which also takes into account the, as you can see, the causal model and the various causal dependencies. I'm not getting into the detail of the reply here, but this is now analyzing both the process model and the causal model. So these are the basics of the kind of services that you can get from our library. And you are invited to play around with it, test it out, and see how it can help you inspect and examine various processes. Thank you. Thank you very much for attending this webinar. I hope I managed to spark your interest in the challenges of automating explainability for organizational processes and how SAX and the SAX library can support this effort through a set of newly developed services.
Thank you very much,
The
Lior, for
presented
this.
research work and developed services are contributed as exchangeable analytics via the FAME platform, where overall the work has received funding from the FAME Horizon Europe project. Thank you. Yeah, now it's the real me.
Thank you. Thank you very much, Leo, for this insightful presentation and demo. I think it was very interesting to learn more about SAX, and I am looking forward to see how it can be applied to real life business processes. It would be very interesting. So, are there any questions? Leo is here to discuss further. If anyone has any comments or questions, you can ask directly or in the chat.
Lior, I have a question. If you can, if you could take a couple of minutes to explain how this fits to the overall business process automation landscape, because there are some exciting developments in this space. So every traditional BPM, BPA or RPA product is now including, some AI functionality. For example, to understand a process that is not working well, or to identify a process from unstructured or semi-structured data. So I was wondering how SAX is positioned against these tools. So is this probably part of a wider suite of IBM in this space? Can it be used in conjunction with some BPA tool where I design my business processes and I track their performance and I have some machine learning, and then I can get SAX to explain it. So what is what is its position in the BPA landscape, and what is the best use of it? So is it the best use to go to the GitHub of Fame and take it and to use it for my processes standalone, or it is best to integrate to some of my BPA, BPM tools? Thank you in advance.
Okay, thank you, John. So definitely the SAX framework is part of the broader area of business automation, which is also the part of the signature of my own email signature. We are all part of that overall effort where we are trying to make business operations more efficient. We are trying to reduce the amount of error. We are trying to reduce the amount of resources and personnel that do the job, so that we can replace it with bots in the virtual domain, and sometimes with the physical robots in the real world. This is all part of trying to make productivity higher with the same level of input going into that. There are lots of tools that are useful in that sense of trying to improve business operations. If you go 15, 20 years back, there was a kind of, in the BPM domain, there was the kind of waterfall perception that we first capture the requirement, then we design the system that has to run the processes, then we run the processes, and possibly we start capturing some exceptions when these processes are executed, so that we can intervene whenever necessary. But if we move forward today, the understanding is that there is no necessarily such real sequencing in the real world. People tend to deploy different technologies in their organizational environments, and they get different employees come with their own tools and knowledge, and everything starts affecting the way that the business is running. And then comes a new manager who wants to understand what's going on and what may be the reason for some malfunctioning parts of the business that may require some attention. So also on that, for this kind of perspective, there is an evolution recently for tools that have been developed more on the process mining side, whether it is trying to make sense of the different business logs of the backend systems, or whether it is task mining when trying to make sense of front-end user actions when interacting with the system. Every part of these technologies are meant to first present a clear picture of what is the true way that the operations are running, and with recent advances with AI, also trying to look forward, look ahead, and predict what might happen in the future, and trying to prevent undesired conditions from happening beforehand, and eliminate the risks. You asked about IBM. IBM has a few tools being developed in that arena. The work that we are doing relates more to the process mining. IBM has a process mining tool, which is like IBM conventional naming, called IBM Process Mining tool. IBM also develops automation on the task, on the user task side. This is in my own team, folks working on what we call UI, no-code UI automation, which is also trying to imitate the activities that the end user are performing on their own laptops and desktop devices. Yeah, and there are other companies doing the same kind of business. I will mention Celonis as one example, who is also leading in that area. And these are, again, all different types of technologies where the intention is to make sense out of the different data that is being accumulated in a way that the people who are running the operations can make sense of it and improve their business.
So in principle, I can use it with a third-party tool. Let me give you an example. I am having, I don't know, Bonita Soft doing BPM, right? And I'm collecting data about the processes. And I have a machine learning that tells me this process is not working well, is ill, right? I could use SAX to explain the outcome of this ML insight.
Exactly. This is what I actually presented. So you can have the log being captured by one process execution engine system that capture that, and then you can have some prediction that telling you that some parts of your instances may be late on the production time, and then you would like to get explanation on what might be the reason for that, and you want to have these explanations clear to people and also sound with respect to what they tell you. So this is all to be integrated jointly into a single cohesive story.
Thank you, Lior. This is very nice. I don't know if we have other questions. We will anyway get the recording, right? Put it on the Fame Learning Center, and we're going to promote this very nice webinar also through the digital channels, because a lot of traffic comes from in this way. Thank you very much for this talk. If there are any other questions, we can take it. Mariana, back to you.
Thank you, John.
Thank you, John. So if there are no other questions, as John mentioned, we will upload the presentation on our YouTube channel and Learning Center. So thank you, everyone, for joining our webinar today. And of course, thank you to Lior, Fabiana, and the IBM team. Stay tuned for more webinars that are coming soon. We will share all the information as soon as we finalize the dates and slots. Thank you again, and have a great rest of the day.
Thank you.
Thank you.
Thank you.